When we draw an organic molecule, we tend to draw it Lewis structure style. Let's do CH4. We put the atom down, we put the electrons around it, we put the other atoms nearby with their valence electrons, and then we pair unpaired electrons between different atoms. Make it look a little nicer, we get our standard CH4. Unfortunately, this drawing, while very handy on paper for very quickly drawing larger, more complex molecules that have covalent bonding, is wildly inaccurate to reality. This shows what appears to be a flat molecule with a bunch of right angles, all 90 degrees. This is nothing like the real shape of the molecule. If you have methane, it is a carbon, one hydrogen goes up, one hydrogen goes over at approximately 109.5 degrees. One hydrogen is going away into the board, and one is coming out at us. So a little force perspective there. And they all have about 109.5 degrees between them. This is 3 points down, 1 point up. Caltrop or various shapes like that. If you have a four-sided dice, if you play Dungeons and Dragons or have board games, it is a tetrahedral. It is a four-sided dice. 3 points down, 1 point up. This is called a tetrahedral. The actual shape is a three-dimensional shape, which the Lewis structures, being designed to draw on paper, are all two-dimensional. So our Lewis structures do not tell us our actual shapes of the molecules at all, and it becomes very important. The shape of the molecule is a major part of how it functions. So how do we translate Lewis structures into shapes? How do we find the geometry, the 3D geometry of a molecule? Conveniently, this is where VSEPR theory comes in. So, looks more like VSEPR, but it is pronounced VSEPR theory. VSEPR theory is a valence shell electron pair repulsion. What this means is the electrons in the valence shell, which when we put together our Lewis structures, it's only the valence electrons, that highest numbered S and P, that end up being used for our Lewis structures. Those electrons, well, they're all negative. They push away from each other. Now, two electrons in a bond, so these two here or those two there, the electrons in the bond can't get away from each other. They both have to be in the same place to be in that orbital. But they can move away from all the other orbitals. And so what happens is if you ever held two magnets near each other, they push away. And if you were holding them in your arms kind of opened. So try this. Put your hands out in front of you together, and then just swing them apart until one is all the way to your right and one is all the way to the left. They've spread out from each other. This is the idea of what's happening with electrons. They are pushing away from the other electrons, from the other bonds and lone pairs. There's only so many ways they can do that. They will try to get as far away as they can. If they kept going, eventually they'd meet on the other side, and so they'll balance out to some point in space. Luckily, those balance points are well known and there aren't too many of them. And so we're going to talk about where they will balance out to. First thing we need to look at is shapes with two things. When I say things, this is atoms or lone pairs. Remember that lone pairs on one atom, like if we think about ammonia, nitrogen has a lone pair. Those electrons came from the valence orbitals. They were part of nitrogen when we built the ammonia molecule. And so they are there pushing the other hydrogens away. Your electrons don't just have to be in bonds to other atoms, they can also be part of valence shell lone pairs. So when we say two things, well, let's think of a molecule that has two things around its center. One of those is carbon dioxide. If we try to build the Lewis structure for this, we'll have carbon with 4, oxygen with 6, and another oxygen with 6. We then try to pair unpaired electrons. We connect everything once, and then each oxygen needs a second, and it can find a second on carbon. Making this look a little nicer, we get carbon, double bond to oxygen, double bond to another oxygen. Now, because those bonds have to go to the same atom, they can't really get away from each other. So those two bonds going to the left oxygen and those two bonds going to the right oxygen, they're not allowed to get apart from each other, but the right oxygen can move away from the left oxygen. And so all the possible ways you could kind of conceive to draw this, if you would put them near each other, well, they would be pushing away. They're always pushing away. Those electrons would shove and try to go that way. These ones would try to go that way. They would spin around that carbon atom trying to get further away. Well, the furthest they can get is on opposite sides. And so they will move to the extreme opposite sides. The result is that you have a shape that basically looks like this, where everything is 180 degrees apart. This makes a straight line with 180 degrees. This is called linear. So a carbon dioxide molecule, because it has two things around the center, is a linear molecule. Well, let's look what happens when you have three things. There's a few examples we'll look at for this one. So we're going to look at BCl3, we're going to look at CH2O, and we're going to look at SO2. Well, boron has 3 electrons, chlorine has 7, chlorine has 7, and chlorine has 7. And so they'd pair, pair, and pair. Boron is an odd element. It's the only element that doesn't routinely have 8 electrons shared. It has an empty orbital. Boron, it's the only element that does this. It's just an odd exception to the rules. Well, as a result, though, boron at the moment has 3 things. It has a chlorine, and a chlorine. And so it will try to spread them out as far as they can get, which ends up being about 120 degrees apart. Boron is flat. It is literally this shape drawn on your screen. It is flat. All the things would be on a piece of paper. It also is sort of triangular. You can kind of see a triangle. So it is a flat triangle. It gets the name trigonal planar. It's a plane. It is a triangle in a plane. It is trigonal planar. CH2O has a carbon with 4, an oxygen with 6, a hydrogen with 1, and a hydrogen with 1. Pair, 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 and pair. You get a carbon, double bond to an oxygen, to a hydrogen, to a hydrogen. That carbon has only 3 things around it. It has the oxygen, it has a hydrogen, and a hydrogen. Now, it has 4 bonds, but 2 of them are to the same thing. And so that oxygen does not count twice. It is a single thing. Well, this has 3 things around it, and just like before, it kind of looks like a triangle. 3 things will be flat. That is the farthest you can get them from each other. And they will be approximately 120 degrees. If you look it up, they are very slightly different. Different atoms, oxygen versus hydrogen, are slightly different in size, and that changes how far they have to get the furthest away from each other. So in a system where everything's the same, like BCl3, they really are 120. Our formaldehyde here in the middle, it's slightly different, but not by much. And so we are only going to ask for the idealized 120 degrees. You will never have to solve the unique real degrees for a real molecule, but they will always be very close to this. Well, this is three things around the center. Again, this is trigonal planar. SO2, I'm not going to draw it all out yet. We haven't talked about third row elements. But short version, I have a double bond to one oxygen, a double bond to a second oxygen, and a lone pair on sulfur. Well, this has three things. Remember, that lone pair counts. It's in the valence. It's pushing the other valence electrons away. And so sulfur has three things around it. They are flat. They're approximately 120 degrees from each other. However, the geometry name is different. Previously, we had three things, and if all three atoms, then we were trigonal planar. In this case, we have three things. Two are atoms. One is a lone pair. This combination has a different name. This is called bent. The reason for this is when we actually see the molecules, we have to shoot X-rays at them. We bounce the X-rays off the atoms in these large crystals, and the angles they bounce off at, we can backwards calculate with a lot of trigonometry to find out how far apart, how big, like how many atoms in what positions and what angles. But unfortunately, those X-rays don't bounce off the lone pairs. And so whenever we actually get one of these structures, we don't see the lone pair. We just see a sulfur and the oxygens below it. And so we can figure out that angle, but we can't see why are they bent down? Why is this not like CO2 and they're straight? The reality is that lone pair is pushing them away. But this just looks like something that's bent. It's not a line. And so it got the name bent. Well, if you can have two things and three things, that means you can have four things. Well, we saw one earlier. If all four were atoms and zero lone pair, this was tetrahedral. This was our CH4. So we had a carbon, hydrogen up, hydrogen over, going back into the board and coming out at us. And so these were all approximately 109.5 degrees apart. And if all the four things are atoms, we called it tetrahedral. But you can have a situation where three are atoms and one is a lone pair. Think NH3. I have my nitrogen, 5, a hydrogen, and a hydrogen. We connect, we connect, we connect. Ammonia. Ammonia has four things around it. One lone pair, 3 hydrogens. It will actually arrange itself showing a dash, but really that's just the lone pair. It's not really a bond to the lone pair. They're on the nitrogen. But I want to just show it in reference to methane. The idea is it still has three things going down. There's a hydrogen, and a hydrogen, and it has one thing going up, a lone pair. Because we couldn't see the lone pair when this was done with the X-rays, all that was observed was a nitrogen and hydrogens below it. Well, this shape kind of looks like a triangle base that goes up to a point. Triangle base that goes up to a point. This looks like a pyramid with a triangle base, and its name is trigonal pyramidal. So when you have four things, three are atoms and one is a lone pair, you will have a trigonal pyramidal molecule. Let's try when we have two atoms and two lone pairs. For this, let's do H2S. Well, I'll have a sulfur. It'll have 6 electrons. I'll have a hydrogen. It'll have 1, hydrogen 1, pair and pair. This gives us 4 things, 2 lone pairs, and 2 atoms. 4 things will try to spread out. And so you'll have a sulfur, say a lone pair up, lone pair going away, hydrogen here, and a hydrogen coming out at us. Well, those lone pairs can't be seen by the X-rays, and so all we really saw was a sulfur, hydrogen, hydrogen. It looked bent again, and so the name for this is bent. If you have 4 things, 2 atoms and 2 lone pairs, your geometry is bent. If you have 4 things, 3 atoms, and 1 lone pair, your geometry is trigonal pyramidal. And if you have 4 things and they are all atoms, you are tetrahedral. Our 3-thing options, well, if all 3 things were atoms, we were trigonal planar. However, if 2 of our things were atoms and 1 was a lone pair, we were bent. And when it came to 2 things, well, the only options here was that there were 2 atoms. And so 2 things, both being atoms, is linear. These are our standard geometries for up to 4 things that we can make using the VSEPR theory to explain how they will move apart from each other. And we can take our Lewis structures and expand them into their geometries. VSEPR theory tells us the electrons and in the bonds and in the lone pairs will try to move as far apart from each other as they can, and these are the geometries in 3 dimensions that they will take that gets them as far apart as possible.